Hi, everyone, and welcome to Engineer Stay. Today, we're talking about this shot from the Stay Over the Rain photo shoot. This was the photo shoot that Stray Kids did for their official fifth fan club launch. In this shot, Changbin appears with this prop. I believe this prop to have been selected because it looks a little science-y, but what actually is it? This is a 3D crystal structure model, and since I have multiple degrees in material science, I can tell you all about it. Most solid materials at the atomic level have a regular repeating arrangement of atoms. This repeating arrangement will fit into one of several different categories, and these categories are called crystal structures. To better understand crystal structures, material scientists will often make models of different structures. The model that appears in the photo shoot is of a crystal structure known as face-centered cubic, or FCC for short. This structure is called face-centered cubic because the corner atoms form a cube, and there are additional atoms in the center of each face of the cube. The model shown in the photo shoot is a ball and stick model, and another rendition of this is shown here. In a ball and stick model, the atoms are shown as smaller than they actually are to help understand atomic arrangements. We will also consider this model, which is called a space-filling model. A space-filling model shows the atoms at full or actual size. FCC is a very common crystal structure, and many metals adopt this structure at room temperature, including aluminum, copper, and nickel, as well as some less common metals like silver, gold, and iridium. Now, you may have noticed that the structure I've shown here does not exactly match the one from the photo shoot. This one has extra atoms here, the blue ones. So, what's going on? This is related to the ability of atoms to fill space, typically referred to as packing efficiency in material science. Some shapes, like squares and hexagons, have 100% packing efficiency, meaning they leave no space between each shape. Other shapes, like circles and triangles, do not have 100% packing efficiency. Triangles, if you are not allowed to rotate them, have only 50% packing efficiency. Another triangle would fit in each of these spaces if you were allowed to rotate them. After some math, we can say that circles have about 79% packing efficiency, leaving these spaces unoccupied. However, you might be able to see that this is not the most efficient packing arrangement of circles. If you align the circles like this instead, then the packing efficiency is increased to about 91%. This demonstrates the arrangement dependence of packing efficiency. In 3 dimensions, the principle is similar. Cubes have 100% packing efficiency, just like squares. However, we will be modeling atoms with spheres. Just like circles, spheres do not have 100% packing efficiency. In an FCC, or face-centered cubic structure, the packing efficiency is about 74%. This means that a significant amount of space remains unoccupied. The atoms in the structure are shown in this space-filling model on the left, and the unoccupied space, known as the void space, is shown separately on the right. If you compare the void space to the model from the photo shoot, you can see that these blue atoms, the extra ones, are in the same place as these little pockets of extra space. These locations in the structure are called interstitials, and they are very important in many materials. Now we have enough information so that we can talk about the error in the structure from the photo shoot. You can see visually, and it can be demonstrated mathematically, that these interstitial spaces are much smaller than the main atoms. In fact, these interstitials can only fit atoms that have a radius about a quarter of the size of the regular atoms. But if you look at this photo shoot structure again, these blue atoms are bigger than the red ones. This arrangement is physically impossible. But everything else about this structure is accurate. And if the atoms were the correct size, there are several materials that form that structure. The most common naturally occurring material with this structure is calcium fluoride, often used as a commercial source of fluoride in drinking water. Other interesting materials include cubic zirconia, which is what imitation diamonds are made out of. Also, uranium oxide, which is often used as a fuel for nuclear power plants. All right, that's all I have for you today. Thank you for watching, and I hope you learned something.